Hi, Lester, Wushu Engineer. It's been a while. Hello to all my faithful subscribers who've stuck around all this time. I hope you enjoy this video. I know I enjoyed putting it together. We only recently got back from our trip to Japan, perhaps a couple of weeks ago now. But we had to hit the ground running pretty hard because the Wushu scientist is still in the middle of her training intervention study. So there's no rest for the wicked, they say. All three of us went to Japan, the Wushu scientist, me and my 9-year-old son, our 9-year-old son Jerry. Going to Japan was a bit of a mistake because now we miss Japan a lot. We had an absolutely wonderful time. The Wushu scientist was honored, as I mentioned in my previous video, with an opportunity to do an oral presentation of our research at the International Society of Biomechanics conference in Fukuoka, and had many good networking opportunities with scientists from Japan and from around the world. We also managed to get around a little bit and see some of Japan as a family in the off times. Alas, there was not enough time in Japan, and now we miss you terribly. Apart from our main mission, which was the conference, the highlight of our trip was unquestionably the overnight ferry trip that we took from Osaka to Fukuoka. I think that we may have been the only Westerners on that ferry, but we felt incredibly welcome. In fact, we actually found Tokyo and our trip to Osaka to be quite stressful. There were a number of reasons for this. It was incredibly hot in Japan at the time of our visit, in the mid-30s most of the time, so that's all day, all night. There were also quite a lot of queues of, in particular, Western tourists at stations and travel departments, and we were carrying pretty big backpacks around with us, and that backpack idea was a bit of a mistake on our part. I thought it was a good idea at the time to get luggage that was in a backpack form, but actually what you get is you get a subpar backpack and subpar luggage. So next time we're just going to go with conventional luggage. But anyway, as soon as we got to the waiting room for the ferry in Osaka, our stress all evaporated. Even though the ferry was actually crowded with Japanese travelers and even several groups of Japanese school kids. We felt very privileged to enjoy the blustery night on the deck of the ship. Jerry loved losing a bit of money at the crane games in the ferry's arcade, and we all loved the meals which were served as a buffet and were umai and sugoi. We had our own cabin with a bathroom and a window or portal, whatever you'd like to call it. While in Fukuoka, we also went to Lalaport, which is a large shopping center that has a massive moving hydraulic model of a Gundam outside. It's fantastic. I have no idea of the cost of such a machine, but it must have easily run into the millions. The Gundam Park, along with the shopping area inside, is absolutely amazing. And in fact, there was this one little section that was specifically for people who were part of the Gundam club or whatever it was. So it had a bunch of monitors on the wall, giving this sort of, well, you could say like an image of a space station with sound effects and Gundams flying across. And then there were all these tables set up, and there was one dude in there who was, I think, working on a little Gundam model, who was obviously a member of the Gundam club, and that's why he was allowed in there. But I thought it was amazing. And I actually really wanted to go back a second time, but unfortunately our time was tightly limited, and my son's need to go a second time to the Fukuoka Pokemon Center to buy authentic, rare Japanese Pokemon cards, that all took precedence, unfortunately. Of course, our main mission was the Wushu scientist's presentation and interactions at the ISB conference. She had an amazing time there, and all of the feedback that she got from her presentation was very positive. We made some very interesting connections with other scientists around the world, which may lead to more research projects and collaborations in future. We certainly hope so. So Japan, if you're listening and you didn't mind us being there, first I'd like to say domo arigatou gozaimasu. I'd also like to request permission to return. So if there are any of the Japan-based scientists and researchers out there who are listening to this and who want us to come back to present more of our research or to collaborate on research projects with you, let us know. We seldom travel purely for holidaying reasons, so a research-related invitation would have to come before we considered shouldering the financial cost of returning. But enough bittersweet reminiscing about our wonderful time in Japan. On to our topic for today. Front kicks, or push kicks, and roundhouse kicks, or curvilinear side kicks, are both very common types of kicks that are utilized heavily in a wide spectrum of martial arts and self-defense based systems. In fact, they're even common outside of civilian martial arts in military combatives curricula around the world. But what do they do? Are they different in terms of what they do to a target, or are they just two slightly different ways to do the same thing? I've heard a lot of people surmising about their differences, debating, some foolishly, others with insight, but without the data to back up their statements. I've heard some people say things like, push kicks are good for knocking an opponent back, while roundhouse kicks are great for breaking bones and doing damage.
This is Sparta!
Well, it's not quite as simple as that. Both kicks are great at breaking things and doing damage. Note that the wood battens used in both of these demonstrations are MGP-10 structural pine battens. Intuitively, martial artists who use both types of kicks can tell you that they're different, with front or push kicks carrying more momentum and roundhouse kicks being more quote-unquote powerful and faster to throw. Of course, people typically use the word powerful incorrectly. So when I use the word powerful in particular regarding results or data that I'm talking about, I'm literally talking about the physics concept of power, which of course is joules per second. It's how much energy is being expended per unit time, or changed, I should say, from one form to another. So I'm talking about the literal definition of power. I would agree with this, because a front or push kick does not benefit from the circular mechanics of a roundhouse kick. It has a smaller effective range of travel and less time to accelerate. So because it has less space and time to accelerate, obviously you would expect that the impact velocity is going to be a bit slower. But because a front kick is more linear and direct, it could be deemed to benefit more from a direct connection to the athlete's center of gravity, perhaps improving its momentum. So how can we determine the actual characteristics of both kicks scientifically? There are not many reliable methods out there to determine the Newtonian characteristics of human impact, because human impact is actually incredibly complex. A human doesn't just represent some kind of simple monolithic mass colliding with another mass. It's a system. A human is a vastly complex mechanical system. And in fact, some of the biomechanics associated with human movement more closely resemble fluid movement, or at least have some of the characteristics of fluid movement, whereas other types of human movement are more purely mechanical in nature. So it's quite complex. It's difficult to model, it's difficult to understand intuitively sometimes, and extremely difficult to measure. However, we at Martel have developed a method which can provide a reasonably reliable and accurate assessment of human impact characteristics, Newtonian impact characteristics. And that is the impulse block method. The full impulse block method allows for a very comprehensive analysis of human striking and has been independently tested for validity and reliability as part of a study by the University of Southern Queensland. In a nutshell, the impulse block equipment consists of a specially designed foam spring called the impulse block, basically slightly squashed cube shape, attached to the front face of a load cell that records force input against time. Using the measured values from the load cell, it becomes possible to calculate a number of characteristics associated with the impacting object. The primary characteristic of interest, in this case, is impulse, or change in momentum imparted by an impact or strike. In addition to measuring the impulse, the full impulse block method involves measuring the velocity of the impacting object at the point of impact, using a microsecond laser photogate timer positioned right at the point of impact with a 1 centimeter gap between the two detectors. Once we have those two values along with the impact duration, which can be determined from the force time curve provided by the load cell software interface, we can calculate the momentum of the impacting object, its apparent or effective mass, the kinetic energy of the impacting object, and the power represented in that impact. For a more detailed explanation of the full impulse block equipment and methodology, you can see my other videos on the subject. I've made many of them. The simplified impulse block method, which is the method that we're going to be using in this video, involves evaluating only impulse and impact duration and not impact velocity. So from that impulse and impact duration, we can determine the momentum of the impacting object or system. This simplified method does not require the use of the microsecond laser photogate timer and simplifies a lot of processing. It allows us to calculate the momentum of the impacting object at the point of impact, and if desired, the impulse data can be fitted to a normalized expected force time curve to calculate expected peak force for specific impact conditions, such as thickness of padding and deformation of the impacting object. Using the simplified impulse block method, it is not possible to calculate the kinetic energy, apparent or effective mass, or the power of the impacting system or object, because impact velocity is required to assess these characteristics. However, the simplified impulse block method still provides us with an incredible amount of information about the impact and the impacting object or system. I will probably default to using the simplified impulse block method in many future videos because we don't always have the time required to do an exhaustive analysis. We are actively involved in a lot of research outside of what you see uploaded to my channel, and a lot of other projects as well. I also think that many of my viewers actually lack the patience to sit through that kind of an exhaustive analysis. So it's a win-win situation, really. But before we carry on, I have to mention the limitations and the errors associated with the impulse block method and system. No scientific tests would be complete without discussing limitations and sources of error. The impulse block method, while the most powerful scientific method that we are aware of to analyze human striking performance, is not without limitations and sources of error. The load cell system that we use digitally samples the force from its load cell at approximately 1 kilohertz, which means that some data, particularly if they occur on sharp force peaks, may be lost, causing measurement errors. In addition, the use of the load cell in conjunction with the impulse block foam spring introduces very strange harmonics into the measurement system, which essentially steals a small fraction of impact energy and thus reduces the measured values for both force and impulse by a few percent. In addition to these sources of error and limitations, several steps in the calculation process are approximations, because an exhaustive mathematical analysis at these points would complicate the calculation process to such an extent that it would no longer be feasible to actually perform quickly and easily. However, despite all of these limitations, we have found after hundreds of repeated drop tests that the error margin on calculated values such as impulse, momentum, kinetic energy, apparent effective mass, and power is under 10%. This error margin is well within the range of performance variation that could be expected from the most well-trained of human combat athletes. So it's not a hindrance to its use in sports science as a reliable and effective method of analyzing human striking performance and in providing feedback for training athletes. I might also add here that over time, the impulse block method could be refined through innovation, use of purpose-made equipment to a point where that error could be all but eliminated. However, that's a project for the future when we hope that the time comes at some stage when the industry accepts the impulse block method as an industry standard of measuring human striking performance. So anyway, we decided to do a short series of tests with me throwing a small set of between 4 and 6 of each type of kick. That's a front push kick and a roundhouse kick, and then choosing the single best example of each of these kicks to perform the simplified impulse block analysis on. This in and of itself is a test limitation. In the interests of efficiency and time, it must be acknowledged. Only a very limited set of tests were performed, and although the waveforms for the kicks were all very similar, only the best 2 results were chosen for analysis and comparison. First, I'll just give a brief discussion of the test setup. So just to introduce the basic impulse block setup that we've got here, you'll notice that the laser photogate timer isn't present. We're not going to do the full impulse block methodology. We're not going to use the full methodology in order to analyze these kicks, just to keep it simple. So all we're going to be looking at are the shapes of the force time curves for these 2 kicks, and then we're going to be applying the simplified impulse block methodology to calculate impulse alone. So we can look at other things like peak force, with the understanding that of course there is a 20 centimeter foam pad mounted on the front of this load cell, which means that the peak force is considerably attenuated by that foam pad. However, as I've mentioned in many of my previous videos, when you calculate impulse, you're actually accounting for, to a certain extent anyway, for the foam padding and any kind of peak force attenuation. The reality is that peak force is essentially an arbitrary value in tests like these because it's so dependent on padding on load cells, the type of object striking the load cell, etc. You can get an incredibly high peak force by dropping a little steel ball onto a bare load cell plate, but that of course doesn't carry a lot of kinetic energy or impulse. So we're looking particularly at the impulse, and of course impulse represents the momentum that the striking object or system is imparting to the system at the point of impact. So it actually represents a characteristic, a Newtonian mechanics-based characteristic of the impacting object or system just prior to impact. So it is an incredibly powerful way of extrapolating information about the impacting system or impacting object, as opposed to just looking at peak force, which is, as I said, essentially an arbitrary value, really, because it's so dependent on the type of system that is set up, type of object that's impacting, and so on and so forth. But as I said, I've mentioned that in many of my videos, so I'm not going to get into a lot of detail here. However, I did want to mention that this is mounted at quite at around about chest height. So it is suboptimal for me to generate peak impact characteristics for both of those kicks. It's of course a lot easier when it's a little bit lower down, and we'll see
people striving to get kick records typically are not kicking at this height. They're kicking at a much lower height because it's easier. So this is a little bit harder to actually get your peak characteristics out there, your peak impulse and peak kinetic energy and that kind of thing. However, it's going to be the same for both of the kicks. So that's actually immaterial, because all we're really doing in this test is in this series of tests is comparing the nature of a front or front push kick to the nature of a roundhouse or side snap kick. Or let's say a curvilinear kick from the side. So that's what we're doing here.
And with that out of the way, this is what the tests looked like. After some number crunching and processing, this is what the best front kick and roundhouse kick looked like in terms of plotting the raw force time curves. As you can see from the plot, the kicks have similar peak forces. However, the front kick has a much extended impact duration. Just a note here though, because presenting these kinds of plots has caused some confusion in previous videos. The impact duration of the front kick, although it is much longer than that of the roundhouse kick, is still only about 1/3 of a second. Just because the plot looks spread out doesn't mean that it's not a quick impact event, as you can easily see from the video footage of the kicks themselves. Now, what we have done in the past is to perform drop tests with various masses, including 20 kilogram and 30 kilogram medicine balls. Although we didn't take any video footage of these tests, we have all of the data. So I thought it would be interesting to do a side-by-side plot of all 4 of these impact events, choosing a single drop test from the 20 kilogram medicine ball and a single drop test from the 30 kilogram medicine ball. And this is what that all looks like. A casual glance at the plots shows that the peak measured forces from the drop tests are much higher than my kicks, and the respective impact durations are much shorter, implying that these drop tests were much higher power events. In fact, the peak forces associated with a 30 kilogram medicine ball essentially came very close to the maximum force that our particular load cell can measure. So we were right at the envelope of the system in terms of drop tests, and we wouldn't want to push it much further than that in terms of peak force. But what about the momentum of those kicks and the medicine balls at the point of impact? How much do they differ? So you'll see the results inset in the screen now, but before I discuss those results, I'd like to draw your attention to the discrepancy between the predicted momentum of the medicine ball drops and the measured momentum. As mentioned previously, there is error and energy loss in the impulse block measurement system. So that's the actual equipment that we're using to perform the impulse block method. And this leads to these kinds of discrepancies. In addition, the medicine balls themselves deform considerably on impact, which also contributes to the discrepancies in measured versus predicted momentum. And yet, despite all of these limitations, sources of error, mathematical approximation methods, and information loss, our measured values are very, very close to the predicted values, deviating by less than 8% from what was expected. I find that quite incredible, actually, and it speaks to the robustness of the impulse block method. Now, looking at the results, despite the clear difference in peak force and impact duration, the front kick had very similar momentum, to the 30 kilogram medicine ball dropped from 1.3 meters. Quite interesting indeed. The momentum of the roundhouse kick was a lot lower though. However, anyone who trains these kicks will be able to tell you that it is actually far harder to commit sustained force behind the roundhouse kick to manipulate apparent or effective mass at the point of impact. So this result fits in with what we already know intuitively about the two different kicks. Now, in the past 6 months, we have performed tests in which we measured the impact velocity of my front kick and roundhouse kick. So in order to discuss these results further, we can use the average velocity as measured in the past for these two kicks. But I must stress that from this point on, we are dealing with assumed values based on previous tests. So these velocities, the velocities for these two kicks, were not measured in this set of tests. So this is an assumption that we're making, that the velocities will be roughly the same. The velocity of the kicks performed for this video may not be the same, so I have to stress this. However, if we make this assumption that the velocity of these two kicks is similar to the velocity as measured in the past, and 6 months ago is how long ago we're talking about here, we can do a full impulse block analysis based on that assumption. So be warned, the following results are speculative and based on the assumption that the velocities of these two kicks were similar to these previous tests. With that caveat firmly inserted, the previous tests performed for these two kicks yielded the following average impact velocities. We can see here that the impact velocity of the front kick is a lot lower than that of the roundhouse kick. It's less than half the impact velocity, in fact. And this again fits in with what we know intuitively about these two kicks. It's hard to get the front kick to accelerate due to the biomechanics in use and the limited range of movement over which the kick must be accelerated. If we assume that the kicks performed for this video have these impact velocities, this allows us to perform the full impulse block method, which yields the following data. Note that I've included the 30 kilogram medicine ball drop from 1.3 meters in this data set because it's actually very similar to the front kick in terms of its impact characteristics. If you have a look at the data, here is where some of our preconceived and intuitive notions get a little challenged. Most of us might assume that because the roundhouse kicks can be so much faster than front kicks, that their kinetic energy will be much higher. However, what we see is that it barely creeps past 50% of the kinetic energy represented in a front kick. So the front kick is a monster on many different levels. This is due, at least in part, to the incredible potential available in a front kick for manipulating and increasing the apparent or effective mass behind the kick. The apparent or effective mass behind a front kick dwarfs that of a roundhouse kick. Another interesting find here is that despite the much higher peak force associated with the 30 kilogram medicine ball drop, its kinetic energy is actually only slightly higher than that of the front kick. The apparent or effective mass behind the front kick was nearly 28 kilograms. So very close to the 30 kilogram medicine ball. This can lead to some extremely interesting discussion about the means that martial artists use to manipulate their apparent or effective masses, essentially to hit as though the limb that's doing the striking weighed a lot more than what it actually did. And that, of course, is related to the fact that a human is a system. So a human can draw from its system to increase their apparent or effective mass during a strike. It's clear that I could not match the peak force of a simple 30 kilogram drop test because I have to remain upright and exert that impact force at right angles to my vertical axis. That's quite difficult. So in order to do that, my peak impact force had to drop, but impact duration could be increased at the point of impact to get a similar effect in terms of energy and momentum to a 30 kilogram mass dropping from 1.3 meters above the ground. I find this absolutely fascinating, and I hope you do too. It's essentially uncovering the hidden biomechanics of combat techniques, because these biomechanical interactions cannot be seen with the naked eye. They represent invisible characteristics like momentum and energy. It's only when we measure these that the shroud can be lifted and we can peer in at what is happening under the surface of a movement, so to speak. As part of our research at Martel, we have performed many physical tests on a variety of participants, some skilled in combat and others not. One of these tests involves testing what kind of sustained forces an athlete can resist from a simple standing position, as I'm standing now. What we've found here is that, barring a few notable exceptions who represent a significant level of skill and training, most people struggle to resist even 5 kilograms or 49 newtons of sustained force, gently and slowly applied to their chests before they become destabilized. So I'll leave you to imagine what the application of nearly 30 kilograms of apparent mass in a 0.325 second impact event localized in the chest area would do to a standing person. Pretty brutal. So it would appear that the humble front kick is not as useless as many people have implied that it might be. The roundhouse kick seems to play second fiddle to the front kick in all but one characteristic: power. You will notice that the power of the roundhouse kick is actually approximately double that of the front kick, and higher even than that of the 30 kilogram medicine ball dropped from 1.3 meters. That's a significant amount of power, all thanks to a very short impact duration and a high impact velocity. So a mixed bag of results in terms of what we intuitively know about these two kicks. But hopefully this information has been of interest to you, and I hope that it can better inform your own understanding of martial arts theory and its associated hidden biomechanical principles. I'll see you all again next time, leave a comment down below if you wish. Leave a like on the video if you enjoyed this content. Cheers.